Right now, your head is aging faster than your feet. That's not a metaphor. It's measured about 90 billionths of a second over your entire lifetime. Gravity is weaker up there, so time runs quicker. And honestly, this is the least disturbing thing I'm going to show you today. Because in 1963, Richard Feynman stared into the math of a black hole and found something that bothered him for the rest of his life. It isn't a hole in space. It's a hole in time. Before we go anywhere near a black hole, I want to prove something uncomfortable to you. Time isn't a clock. Time is a substance. And right now, it's on your body, in your pocket, and inside a stairwell at Harvard. Start with your pocket. About 12,550 miles above your head, a GPS satellite is running 38 microseconds faster every single day than the clock in your phone. Let me say that one again, because it's easy to blow past. 38 millionths of a second. Every day. Forever. The satellite is younger than your phone. On a schedule you could set a watch by. Why is it faster? Because gravity is weaker up there. Less gravity tugging on that satellite's atomic clock means time itself, the thing the clock is trying to measure, is running a hair quicker. Here's what that means in the actual world you live in. If engineers did not correct for that 3/8 microsecond daily drift, Google Maps would put you about 7 miles off by lunchtime. Your phone would be useless by dinner. You'd be ordering takeaway from a restaurant 3 postcodes over and not know why. This is not theory. This is not a thought experiment. Every time you open Maps, you are using Einstein's general relativity. The software in your pocket is silently correcting for bent time while you order coffee. You have been using a relativity engine for a decade and probably never noticed. Time isn't something you read. It's something you carry. So, when did we first catch time bending in the act in a building? 1960. Harvard University. Inside the Jefferson Physical Laboratory. The experiment is almost embarrassingly modest. A tower, 22. 5 meters tall. About 74 feet. 7 stories. Not a satellite. Not a particle accelerator. A stairwell. 2 physicists, Robert Pound and Glenn Rebka, shot a beam of gamma-ray light up that tower and measured how much the light's frequency shifted just from climbing out of Earth's gravity. That is all. Light goes up. Check whether time treated it the way Einstein said it would. What did they find? The light's frequency shifted by 1 part in a quadrillion. A 1 followed by 15 zeros. A shift so tiny, most people would call it a rounding error. And yet, they caught it. Cleanly, repeatedly, inside an ordinary building. Think about that for a second. The math said time should bend inside a Harvard stairwell, and it did. Same math. Same physics. The GPS satellite above your head is just the Pound Rebka Tower, scaled up by about 900,000. A stairwell. A satellite. Same trick. Which brings us back to the warm-up. Remember what I said at the top? Your head is aging faster than your feet. About 90 billionths of a second over your entire lifetime. That is the Pound Rebka experiment, running for free on your own body every second you've been alive. Your head sits 5 or 6 feet above your feet. Gravity is a hair weaker up there. And your brain, all day, every day, has been living a few trillionths of a second in the future relative to your toes. You are standing in a gravitational gradient. Your body is being sliced into time zones. So if time can bend inside a Harvard stairwell and on the frame of your own skeleton, what does it do somewhere gravity is truly ferocious? Let's not go up this time. Let's go down, deep down, to the center of the Earth. Right now, the center of the Earth is about 2.5 years younger than the ground you are standing on. Let that sit for a second. Not younger in some poetic sense. Younger by the clock. If you could take a pocket watch down through 6,378 kilometers of rock, about 3,960 miles, to the molten iron core, leave it there a while, and then bring it back up, it would be behind your wristwatch by roughly 5 years. Why? Same reason as the pound Rebka tower, just flipped upside down. Down there, buried under nearly 4,000 miles of mass, gravity squeezes harder. And when gravity squeezes, time slows. Every tick down at the core is a fraction of a tick shorter than your tick up here. Here's the line I honestly can't get out of my head. Every second you've been alive, your feet have been living in a slightly older timeline than your head, and the Earth's molten heart has been living in an older timeline than either of them. You are not a single point in time. You are a gradient. Physics isn't out there. Physics is touching you in every direction at once. Now scale this up. If time bends on a planet, inside a stairwell, on a skull, what does it do across the whole universe? In the 1920s, astronomers noticed something bizarre. The farther away a galaxy was, the more its light was shifted toward the red end of the spectrum. Every single distant galaxy. All of them. Redder the further out you looked. You've heard this effect before, in a different form. An ambulance siren. When it's coming toward you, the pitch is higher. When it's going away, the pitch drops. That's the Doppler effect for sound. Waves bunch up coming at you. They stretch out, going away. Light does the exact same thing. Redder light means the source is moving away from you. So here is what the sky was telling us, loud and clear, in every direction at once. Every galaxy out there is moving away from every other galaxy. Everywhere. All the time. Space itself is stretching. The universe is not sitting still. It is actively running away from itself. And if space is stretching now, what does that mean for yesterday? Smaller. A week ago, smaller. 1,000,000 years ago, much smaller. 1,000,000,000 years ago, very small indeed. Run the movie backward far enough. Run it all the way. And every galaxy, every star, every atom, every version of you is packed into a single point. The Big Bang was not an explosion in space. The Big Bang was an explosion of space. There was no outside for it to explode into. Space itself inflated, and it is still inflating right now around us. As you're listening to this, which means something important, and this is the thread we're going to pull for the rest of the video. If space can stretch, expand, and unfold from a single point, then so can time. Time is not the stage. Time is a character. Time can bend. Time can stretch. And as we are about to see, time can rip. But what happens to that character? Time. When gravity becomes so strong, it doesn't just bend it, it breaks it. For that, we need to zoom in. Way in. Past galaxies, past planets, down to a single dying star. So, space can stretch. Time is a substance. And somewhere out there, gravity is ferocious enough to tear that substance apart. But before we fall into one star, one quick side trip. Because the same tug of war that decides what happens to a dying star decides what happens to the entire universe. Our universe has 3 possible endings. Just 3. And physicists have been arguing about which one we're in for the better part of a century. Fate 1, expansion wins. Forever. The galaxies keep flying apart. Stars burn out one by one. The lights go out. The last black holes evaporate in about 10 to the 100 years. We call this the heat death. It's cold. It's dark. It's empty. And it is quietly the most likely outcome based on what we measure today. Fate 2. Perfect balance. A flat universe sitting on a knife edge. Expansion and gravity cancel each other out exactly. Nothing collapses. Nothing runs away. It just coasts. Fate 3. Gravity wins. The big crunch. The expansion reverses. Galaxies rush back together. Space itself contracts. Every atom, every star, every version of you packed back into a single point. A universe that began in fire ends in fire. Here's the line I want you to carry. All 3 of those futures depend on one argument. Gravity versus expansion. And that exact same argument, gravity versus something pushing back, plays out inside every single star in the sky. A dying star is a universe in miniature. Same fight. Same 3 endings. A star, any star, is basically a very slow argument. Fusion is pushing outward. Gravity is pulling inward. For billions of years, they balance. That balance is what we call a star. That's it. Then, one day, the fuel runs out. If the star is small, sun-sized, give or take, gravity wins gently. The outer layers drift off. What's left is a white dwarf, a slowly cooling ember about the size of the Earth that will sit in the dark for trillions of years. Quiet, sad, fine. But if the star is big, a few times the mass of our sun, gravity wins brutally. The core collapses so fast that electrons get crushed into protons. You don't have atoms anymore. You have a ball of pure neutrons, about 12 miles across, spinning hundreds of times a second. And here's the number I honestly don't know what to do with. A single teaspoon of neutron star material weighs about 6 billion tons. 1 teaspoon. 6 billion tons. Mount Everest in a coffee spoon. That's not the end of the ladder. That's the rung before the edge. In 1930, a 19-year-old physicist named Subramanian Chandrasekhar was sitting on a boat, sailing from India to Cambridge, England, doing the math on what happens when a dying star gets really, truly big. He found a limit. A hard one. Today we call it the Chandrasekhar Limit. If the collapsing core of a star is more than about 5 times the mass of our sun, nothing stops it. Not fusion, not electron pressure, not neutron pressure. Not one single force that humans have ever discovered. Think about that for a second. We know every force in the universe. We have lists of them. We've measured them. And at 1, 5 solar masses of collapse. We are past all of them. So what does a star collapse into when nothing in the universe is strong enough to stop it? For decades, we didn't have a word for it. We have one now. And the person who gave us the math for that word was, at that exact moment, dying in a trench on the Russian front in 1916. His name was Karl Schwarzschild. And his story, I think, is the part of this video you will remember the longest. November 1915, Albert Einstein publishes General Relativity, the full equations, tensors, 10 coupled differential equations. Most physicists of the day take one look and decide they'll think about it after the war. Karl Schwarzschild is 41 years old, a brilliant German astrophysicist, director of the Potsdam Observatory. When World War I breaks out, he does something that, looking back, makes almost no sense. He volunteers. 41-year-old, world-class scientist, volunteers for the German army. By 1915, he's on the Russian front, serving as an artillery officer. And in the trench, he is also dying. Slowly. A rare autoimmune disease called pemphigus. His own immune system is attacking his skin. He is, literally, being erased from the outside in. And in that trench, under artillery fire, in pain, months from the end of his life, Schwarzschild gets a copy of Einstein's new paper. And within a few weeks, he does the thing nobody else on Earth has managed to do yet. He solves it. He finds the first exact solution to Einstein's equations for the simplest possible case, the gravity around a single point of mass. He mails the paper to Einstein. Einstein writes back, stunned. His words, quoted almost everywhere since, "I had not expected that the exact solution to the problem could be formulated so simply." 4 months later, Schwarzschild is dead. He is 42 years old. He never lives to see what he has found. Which is, though he doesn't know it, the mathematics that describes every black hole in the universe. A man dying in a trench sized the shadow of a black hole 100 years before anyone could see one. What he found, we now call the Schwarzschild radius. It's the boundary where his equations go, frankly, insane. Time terms flip. Space terms flip. The math tells you, very clearly, you have crossed a one-way door. And that boundary has a specific size for any given mass. For the sun, if you could somehow crush our sun down to a sphere about 3 kilometers across, roughly 9 miles, it would become a black hole. The whole Sunday, a neighborhood. For Earth, 9 millimeters, 0.35 of an inch, the size of a marble. If something tomorrow crushed our planet down to a marble, we would not die from the crushing. We would die because time itself, at the surface of that marble, would stop. Schwarzschild saw all of this in 1916, in a trench, dying, and he never got to ask the obvious next question. The one that Richard Feynman would walk into 47 years later at Caltech and refuse to let his colleagues dodge. What happens to a person who crosses that boundary? What does time do to them? And what does it do to us? Watching from the outside with a telescope in our hands? Let me walk you down the ladder, one rung at a time, until we are standing right at the edge, and someone we love is about to step off. Schwarzschild handed us the math in 1916. Dying in a trench, never seeing a single black hole. So let me walk you down his ladder. One rung at a time. And I want you to notice something as we go. It's not space that gets stranger with each step. It's time. Rung 1. Stand on the surface of the sun. Pretend for a second you could. Time, for you, would run about 2 parts per million slower than it does for someone watching you from Earth. 2 millionths. Tiny. But already measurable. Gravity is bending your clock. Rung 2. Drop down onto the surface of the moon. Less mass. Less gravity. Time there runs a hair faster than on Earth. About 57 microseconds per day faster. That's why NASA, right now, is literally building a special timekeeping system just for the moon. Because what time is it on the lunar surface is not the same question it is down here. Rung 3. Back to Earth. Walk outside. The difference in time between the roof of your house and the floor of your basement is real. It's measured. It's small. Picoseconds. But it exists. You live every day on a tiny gravitational slope of time. 3 rungs. 3 planets. Same substance bending in 3 directions. We've only walked down 3 steps. Schwarzschild's ladder has at least 6. Rung 4. Take everything you know, the whole Earth, and crush it to the size of a marble. 9 millimeters. That is the Schwarzschild radius of our planet. At that boundary, time doesn't slow down a little. Time, for an outside observer, stops. Let me say that again. If you are standing on this new marble Earth and your friend is watching from a safe distance in orbit, your wristwatch from their telescope appears frozen. Not delayed. Frozen. Rung 5. Now do the same to the Sunday. Crush it down to 3 kilometers across. About 1. 9 miles. Same story. Bigger marble. Same frozen clock at the surface. And now, this is the one that stops people. Rung 6. Take a small star, roughly 10 times the sun's mass, and let it collapse under its own gravity. Nobody crushes it. The star does the work itself, in a few seconds. What it collapses into. The mathematical object at the center has a Schwarzschild radius of about 30 kilometers. And this is no longer hypothetical. These objects exist. They are up there, right now. We have a name for that outer boundary, that last rung of the ladder. We call it the event horizon. It is not a wall. It is not a hole. It is a line, a perfectly invisible sphere, where the math Schwarzschild wrote down in a trench does something weird. The equations that describe time and the equations that describe space swap places. Inside that line, moving forward in time, is the same mathematical operation as falling toward the center. You don't fall because gravity pulls you. You fall because time keeps going forward. And forward now points down. There is no way back. Not because you're not strong enough. Because the future is in one direction, and that direction is the center of the black hole. Which sets up the cruelest, most beautiful question in all of physics. If time itself leans toward the center, what happens to a person falling in? And what do we, holding the telescope, see? Okay, close your eyes for a second. Do this with me. Someone you love, pick a face, is an astronaut.
8
They are in a small craft, drifting toward the event horizon of a black hole.
0.
You're 1,000,000 miles away, safe, watching through a telescope. You wave. They wave back. Here is what you see from your side. As they approach the edge, their wave starts to slow down. Not metaphorically, literally. The video signal is running at a weirder and weirder frame rate. Their voice drops in pitch, like a cassette tape being played too slow. The last word they say stretches out over seconds, then minutes, then hours. You watch their last wave take a year to finish, then a decade, then 1,000,000 years. Their image goes deep red, then infrared, then invisible, not because they moved, because time, on their end, from your point of view, has slowed to something approaching 0. They never fall in, not from where you are standing. For you, they are frozen, forever, on the edge of the horizon. A person suspended in a single moment that will never finish. That is your story. Now let me tell you theirs. From inside their craft, from their own point of view, nothing weird happens at the horizon. They cross the line. Their clock ticks. Their heartbeat carries on. They look out the window and see the universe behind them. You, the telescope, the stars, all slightly blue shifted, slightly sped up. But fundamentally, they are still them. Still alive, still falling. And from their point of view, the fall from the horizon to the singularity at the center is not eternal. It's fast. For a stellar mass black hole, they reach the center in under a fraction of a second. For a supermassive one, maybe a few hours at most. Finite. Over. Done. They didn't freeze. They didn't stretch. They just fell in. The way you'd fall off a diving board. 2 people. 1 event. 2 completely different stories. And here is the thing I need you to sit with. Both stories are correct. Both are measured, predicted, and confirmed by the same Schwarzschild equations from 1916. This is not a paradox to solve. This is a paradox to believe. This is what Feynman walked into at Caltech in 1963. Not the spectacle of a black hole. Not the CGI. This. The mathematics saying 2 opposite truths about the same person are true. In the same universe. At the same moment. From outside, they are frozen forever. From inside, they are gone in an instant. That is not a glitch. That is not an error bar. That is not something we'll fix with a better telescope. That is what time becomes when you squeeze gravity hard enough. A black hole is not a hole in space. A black hole is a place where time has been ripped into 2 contradictory pieces. And both pieces are real. Which, if you are paying attention, means something extraordinary about us. About the universe we live in. About every clock you have ever looked at. Because if time can be ripped in 2 out there, why do we trust a single timeline down here? That question, the one Feynman chased for the rest of his life, opens the door we are about to walk through. So a black hole takes one event and breaks it into 2 true stories at the same time. Fine. That's out there. 1,000,000 miles away. Not your problem. Except, and this is the part Feynman kept chewing on for the rest of his life, the universe doesn't have a faraway button. The same physics runs everywhere, including the room you are sitting in. Here is the awakening I want you to have. You are not on a single timeline. You, right now, are a bundle. Your head, as I said at the start, is aging faster than your feet. Your right hand, if it's raised above your heart, is aging a sliver faster than your left. Every cell in your body is running on a slightly different clock, because every cell sits at a slightly different height in Earth's gravity. There is no master now for you. There is no single instant shared by all of your atoms. Let me say that the other way, because it's worth hearing twice. The you think of as one person, frozen in a single present moment, doesn't exist. Physically, it's a summary. Your brain stitches it together because thinking of yourself as a bundle of slightly out-of-sync clocks would be unbearable. So it smooths it. It lies gently to keep you sane. But the truth underneath is, you are already doing what an astronaut does at an event horizon. Just very, very slowly. The hole in time is not only out there. There is a tiny, everyday version of it living inside you. Fact 1. Every time your phone tells you the time, it has just corrected for relativistic drift from a satellite 12,550 miles above you. You agreed. You tapped the icon. Fact 2. Every time you take a flight, San Francisco to London, say, the people on that plane come back about 10 nanoseconds younger than they would have been if they'd stayed on the ground. Measured. Real. Jet lag in the deepest possible sense of the word. You agreed to that too when you booked the ticket. Fact 3. Every time a cardiologist does a PET scan of your heart, the positrons they're firing at you and detecting are only possible because time, mass, and energy are the same substance. E equals mc squared is not a poster on a classroom wall. It is the reason the machine can see you're still alive. You have been living inside Schwarzschild's universe your whole life. You just weren't told. If you've never noticed relativity, that's not because it's absent. That's because it's intimate. And this is what Feynman kept coming back to. Not the spectacle of black holes. Not the math. This. If time can be ripped in two for a falling astronaut, and if time is already a bundle, not a thread, inside your own chest, then the most normal sentence in English, right now, is not a fact about the universe. It's a fact about your brain. Ugh. And once you see that, a quiet thing happens. You stop being a passenger in time. You start being a participant in it. You start paying attention to which rung of the ladder you're standing on. But, and this is fair, I'm asking you to believe a lot right now. So before we go any further, let me put the receipts on the table. Every one of them. And let's see if this still holds up. Receipt 1. The one in your pocket. GPS. A 3-1 satellite network, each carrying a cesium atomic clock, each running 38 microseconds per day faster than ground clocks. Engineers discovered this is not a glitch. It is a daily correction every GPS device on Earth performs, silently, to avoid Google Maps drifting 7 miles by lunchtime. If Einstein was wrong, your phone would be useless. Instead, 1 billion phones confirm him every morning. Receipt 2. 2010. National Institute of Standards and Technology, Boulder, Colorado. 2 optical atomic clocks, accurate to 1 second in about 3. 7 billion years, were placed on 2 lab benches 33 centimeters apart vertically. About a foot. They measured the time difference between the higher clock and the lower clock, and they caught it. Time was running measurably faster on the upper shelf than on the lower shelf. In a basement, in Colorado, on shelves that were 1 foot apart. Schwarzschild's math, operating on the scale of your bookcase. 1 foot of height. Measurable time difference. We caught the universe bending on a shelf. Receipt 3. Pulsars. These are neutron stars. The rung below black hole on Schwarzschild's ladder. That spin hundreds of times a second and beam radiation at Earth like a lighthouse. They are the best clocks in the known universe. For over 50 years, radio astronomers have tracked binary pulsars, 2 of them orbiting each other, and watched their orbits shrink, year by year, at exactly the rate general relativity predicted. Exactly. The 1974 Hulse-Taylor pulsar matched Einstein to better than 0. 2%. Nobel Prize 1993. Receipt 4. 2015. LIGO, the Laser Interferometer Gravitational Wave Observatory. A pair of 4-kilometer long L-shaped detectors in Louisiana and Washington State. On September 14th, at roughly 9:50 UTC, they felt a ripple pass through the Earth. A ripple in space-time itself from 2 black holes, 29 and 36 solar masses, merging 3 billion light-years away. The ripple physically stretched and squeezed those 4-kilometer arms by about 1/10,000th the diameter of a proton. And they caught it. Time and space are a fabric. We just heard the fabric ring. 5 years later, Nobel Prize. 2 years after that, we started seeing black holes collide monthly. Receipt 5. April 10th, 2019. The Event Horizon Telescope collaboration. 8 radio telescopes across 4 continents, wired together into a virtual dish the size of planet Earth. Released a single photograph. M87. A supermassive black hole in the heart of a galaxy 55 million light-years away. 6. Breath. 5 billion times the mass of our Sunday. And at the center of the image, a dark circle surrounded by a glowing ring of hot gas. That dark circle was the shadow of an event horizon. Schwarzschild's math made visible, for the first time in history, 103 years after he died in a trench, without ever seeing one. 5 receipts. 5 completely different instruments. 5 completely different teams. 1 answer. Time is a substance. Gravity bends it. And at enough gravity, it rips. So the evidence is in. The math holds. The photograph is on the wall, which leaves only the hardest question of all, the one that still keeps physicists awake at night. Deeper mystery. So the receipts are on the table. 5 instruments. 1 answer. Time is a substance. Gravity bends it. At enough gravity, it rips. Fine. Case closed. Except Feynman never closed it. Because when you follow Schwarzschild's equations past the horizon, all the way down to the center, the math doesn't just get weird. It breaks. At the very center of a Schwarzschild black hole, the equations predict a point of 0 volume and infinite density. We call it a singularity. And let me be honest with you about what that word means in physics. It doesn't mean a tiny dot that's really, really dense. It means our math ran out. When an equation gives you infinity as an answer, the equation is not telling you a fact about the universe. It is telling you it has quit. It has walked off the job. It is saying, I was designed for space-time, and I no longer know what space-time is at this point. Every tool we have, general relativity, quantum field theory, the entire standard model, all of them hit that center and scream the same word. Infinity, which is not an answer, which is a vacancy sign. Something is there. We just don't have the math yet to describe it. A black hole isn't just a hole in space. It's a hole in our physics. Stephen Hawking, 32 years old, Cambridge University. He takes the one place in the universe where relativity and quantum mechanics both have to work at once. The event horizon of a black hole. And he does the math. And he finds something that stunned everyone, including himself. Black holes are not perfectly black. They glow, faintly. Because of quantum effects at the horizon, they leak radiation, now called Hawking radiation. And over unimaginably long timescales, they evaporate. A black hole the mass of our sun would take about 10 to the 67 years to disappear. That is a 1 followed by 67 zeros. Far longer than the current age of the universe, which is only 10 to the 10 years. But eventually, if you wait, it goes. Fully. Gone. And here is the question that made physicists start shouting at each other. If the black hole ate an entire star full of information, trillions of atoms, each with a specific position, spin, history, and then the black hole evaporated into a fog of radiation, where did the information go? Nature keeps receipts. Everywhere. Except, apparently, here. This is the information paradox. And it is still unsolved. Today, in 2026, quantum mechanics has one absolute, non-negotiable rule. Information is never destroyed. You can scramble it, burn it, shred it, feed it to a star. Some genius with enough instruments could, in principle, reconstruct it. Always. Except at a black hole, where the math, best we can tell, lets the receipts vanish. That is what Feynman walked around Caltech chewing on in 1963. That is the question Hawking, Susskind, Hooft, Maldacena, and dozens of others spent careers on. Nobody has fully closed it. There are candidates: holographic principle, firewall, soft hair theorem. All elegant, none proven. Which means the hole in time we've been talking about, this entire video, may also be a hole in the universe's memory. Which is exactly where a careful viewer, and I hope you are one, should push back hard. So let me do the pushback for you. 3 objections. Out loud. I've been handing you big claims for 30 minutes. Time is a substance. A black hole rips it. Information may vanish. You deserve the other side. Here are the 3 strongest objections I can build against what I just told you. Objection 1. A sharp physics student might say, the freezing of a falling astronaut that we see from outside versus their instant fall from inside. That's a coordinate artifact. Different observers. Different frames. No actual ripping. Just math bookkeeping. Fair. Partially true. In Schwarzschild coordinates, yes, the split looks extreme. Switch to Kruskal-Shekera's coordinates. A different mathematical chart. And the infall becomes smooth. But, and this is the part that matters, no matter what coordinates you choose, the horizon is still a one-way membrane. Light cones still tilt. The future of the infaller still points inward. The fact that different observers build different histories of the same event is not fixed by changing charts. It's a real, physical feature. The rip may be a framing choice. The divergence of experience is not. You can redraw the map. You can't redraw the territory. Objection 2. This is just math. Nobody's actually seen time break. Also fair. Nobody has ridden into a black hole with a stopwatch and come back to post about it. But remember what we built in the evidence fortress. Every falsifiable prediction of this same math has been checked and passed. GPS drift, 38 microseconds a day. NIST tabletop clocks, 33 centimeters apart. Hulse-Taylor pulsar, 0. 2% agreement over 50 years. LIGO catching ripples from merging black holes. EHT photographing the shadow of one. If the math that is right about all of those things, dozens of independent tests, a stack of Nobel Prizes between them, is wrong only at the horizon, we need a reason. We don't have one. Absence of a direct infall experiment is not absence of evidence. It is a gap we haven't filled. Yet. Objection 3. Fine. But this is out there. It has nothing to do with me. This is the quietest objection. And it's the one I care about most. Because if you carry only one thing out of this video, I want it to be the answer to this. You are already standing in bent time. Your head is aging faster than your feet, 90 billionths of a second over your lifetime. Your phone corrects 3/8 microseconds of relativistic drift every morning. NASA is building a separate clock for the moon because what time is now depends on where now is. A black hole is not a different physics. It is the same physics, turned up to full volume. The difference between you and the horizon of M87 is not kind. It is degree. You are a small version of that event, running in slow motion for 80 or so years. That is the receipt. And it is you. So, if the universe is bending your time, right now, and if a black hole is just the extreme version of what your body is already doing, what do you do with that? What changes on a Tuesday morning because of this? So, Tuesday morning, you wake up. Coffee, phone, work. What actually changes? Because a German scientist solved Einstein's equations in a trench in 1916, and a black hole 55 million light years away is bending time into 2 stories at once. 3 things. Small, concrete, free. First shift. The next time you catch yourself saying, right now, add a location in your head. Right now, here. Because now on your watch is not now on the moon. It is not now at the center of the Earth. It is not now on the M87 horizon. NASA is building a separate clock for the moon exactly because now is a local phenomenon, not a universal one. That one tiny habit, right now, here, is physics level accurate. And it's free. One word. 0 cost. Instant upgrade to how you see reality. Second shift. When you stand up from your desk tomorrow, just notice. Your head just moved into slightly faster time. Your feet stayed in slightly slower time. Nothing mystical. 90 billionths of a second over a lifetime. But the act of noticing does something the physics can't do for you. It turns your body into a participant in relativity, not a bystander to it. Every time you climb stairs, you are doing a tiny pound Rebka experiment. Every time you fly, you are a Hafele Keating clock. You are not in the audience of physics. You have been on the stage the whole time. Third shift. And this one is strange. Impatience gets harder to justify. Because if time is a substance, not a metronome in the sky, then "I'm running out of time" is not the same sentence it used to be. Your time isn't ticking away on some universal master clock. Your time is the specific, local, bent, stretched substance that your particular body is carrying through Earth's gravity well. You don't lose it. You spend it. On this conversation, on this Tuesday, on the mug in your hand, and once you see time that way, as a substance you are holding, not a sentence being handed down, something loosens. Which is, I think, the thing Feynman was actually chasing. Not the math, the permission. Let me show you what I mean. In 1963, at Caltech, Richard Feynman wasn't the first person to see the dual point of view paradox of a black hole. Schwarzschild found the math in 1916. Oppenheimer worked out stellar collapse in 1939. Wheeler coined the phrase black hole in 1967. Feynman was late to the table. What Feynman did, and this is why his lectures still land 60 years later, was refuse to treat the observer as a ghost. He kept asking, who is watching? From where? With what clock? What does their version of the story look like? He dragged the human body back into physics. He put you inside every equation. That is the real disturbing discovery. Not the hole in time. The fact that you're inside it. Here is the single question Feynman's approach hands you for free. Not what is happening. Not what time is it. But where am I standing? And what does the event look like from here? Ask that about a black hole, and you get two truths and a ripped timeline. Ask that about your marriage, your career, a fight you had last month, the last conversation with your father, and something uncomfortable happens. You realize there is no single master what really happened. There is only what happened from where you were standing, and what happened from where they were standing. Both of those are real. Both are measured. Neither is a lie. That is the permission Feynman was chasing. Not the equations. The posture. You are not a passenger in time. You are not a passenger in your own life. You are standing on a specific rung of a gravitational ladder, watching a specific slice of the universe, carrying a specific clock. You are the experiment. You always were. And the question, where am I standing, is how you stop being a specimen and start being a scientist. Which is exactly the door I want to walk you through one last time before we close. Before I let you go, let me walk you through the whole cathedral. One time, in under 2 minutes. So when you close this video, the shape stays. A Harvard stairwell, 1,960. Two physicists shoot light up 7 stories and catch time bending by 1 part in a quadrillion. That is image 1. A German astrophysicist dying in a trench in 1916 solves Einstein's equations under artillery fire and mails the math that describes every black hole in the universe. Image 2. Someone you love crosses the horizon of a black hole. From outside, frozen forever. From inside, gone in a fraction of a second. Both true at once. Image 3. A photograph, April 2019, of the shadow of a supermassive black hole 55 million light-years away. Schwarzschild's math made visible 103 years after he died without seeing one. Image 4. And finally, you, standing up from your desk. Your head, for the next 80 years, living in very slightly faster time than your feet. Image 5. 5 images. 1 spine. You are on it. Here is the single line that holds them all. Time is not a backdrop. Time is a substance. Gravity bends it, stretches it, and at enough gravity, rips it into 2 true stories at once. From a Harvard stairwell to the M87 horizon to the space between your ears and your shoes, it is all the same physics, different volume. A black hole is not a hole in space. It is a hole in time. So the cathedral is built. 5 images, 1 spine. Time is a substance. Gravity bends it. At enough gravity, it rips. Which leaves only the thing I promised you at the start. I opened this video telling you your head is aging faster than your feet. 90 billionths of a second over your entire lifetime. That was the least disturbing thing I said. Now you know why. Because the same physics that makes your skull tick a hair faster than your heels is the physics that, at enough gravity, takes one person falling past an event horizon and gives them 2 different true lifespans. On the same Tuesday, in the same universe, at the same moment. A black hole isn't a hole in space. It's a hole in time. And the GPS satellite 12,000 miles above your head is the receipt. Here is what I hope you carry out of this. You are not a passenger in time. You are standing on a specific rung of Schwarzschild's ladder. Right now. Watching a specific slice of the universe. Carrying a specific clock. That is not poetry. That is physics. And it is yours. If that shifted anything for you, even a little, do the thing that helps this channel keep building cathedrals. Subscribe, and leave the 1 image from this video that stuck in the comments. Not for the algorithm. For the next person who needs this. See you on the next rung. Ha.